Okay, now I want to wrap up the week by returning to an earlier model we looked at, the associative model. How is the intercept and slope of one outcome related to the intercept and slope of another variable? This week I want to introduce 3 ways, more than the associative model, for looking at that. Next week we'll actually learn how to run these, which are called multivariate or higher order growth models. So ignoring the fine print, literally, this is one of 3 models discussed by Bolen and Curran. This one looks a lot like what we did earlier, except more complicated. This is the associative model. What do we have here? Adolescents measured over 4 occasions and asked about alcohol, tobacco, and marijuana use over time. All 3 go up in adolescence. And here we have lots and lots of associations between the growth models for alcohol, tobacco, and marijuana. Basically, every intercept and slope is allowed to relate to every other intercept and slope. Now, if you zoom in, you'll see that there are some extra constraints, odd things like the mean and variance of each intercept and slope forced to be equal, and the correlations among them all to be forced to be equal. Those are identifying constraints for a particular version of the associative model that we'll dive into more next week. Bolen and Curran introduce these constraints so that we can compare model results from this model to 2 other models. Now, this is the factor of curves latent growth model. First, let's look at what it does, which is conceptually simple. There are 3 growth curves, one for alcohol, one for tobacco, and one for marijuana, just like the last slide. But then the model goes and introduces a second-order intercept and a second-order slope. And all the lower-order intercepts load on the higher-order intercept, and all the lower-order slopes load on the higher-order slope. And this is a way of testing whether there's a single common growth process, let's call it tendency to use substances in general, that explains growth in all 3 parameters. Now again, the letters in these diagrams imply all kinds of constraints, variances forced to be equal over time, and so forth. Those are identifying constraints and also permit us to compare this model to the special associative we just looked at in the last slide. And we'll get into the nitty-gritty of all that next week. Why is it a factor of curves? Because it's a higher order factor model built on 3 lower order curves. The factor is built on top of the curves. The alternative is curve of factors. Now, this is very different, because here we have 4 lower order factors, and they are different from anything we've done this semester. A time 1 factor made up of alcohol, tobacco, and marijuana at time 1. A time 2 factor made up of alcohol, tobacco, and marijuana at time 2, and so forth. And on top of these 4 time-specific factors is built a higher order growth curve, a common intercept and slope. Again, the constraints are to facilitate model comparisons, and we will follow that next week. But again, this is a curve of factors because the higher order curve is built on 4 lower order factors that are time specific and not on curves themselves. Analytically, this is often the easiest to set up and often fits best, but we'll get into the technical differences later. What all 3 share in common is some expression of common shared intercept and slope, identifying a higher order process that explains why growth occurs in multiple lower order processes. I'll show you some paper examples in a few minutes to concretize this. So this table compares intercept and slope, fixed mean, random variance, and covariance across the factor of curves in red and the curve of factors in blue. And a cursory inspection shows that they produce largely similar findings overall regarding intercept and slope, with slightly less variance in the curve of factors approach, which might indicate that the curve of factors produces a better fit to the model. But as Bolen and Curran note in the final sentence on this slide, based solely on statistical comparison, selecting a superior model is difficult. Once you've got these models, then you can run conditional models trying to predict these higher order growth processes. This example shows age predicting coupled intercept and slope in an associative model. And what Bolin and Curran did here is show the effect of age on intercept and slope in the associative model in red, the factor of curves in blue, and the curve of factors in green. And the take-home here is that regardless of approach, we see age-related effects on intercept. The older you are, the more you use, but non-significant negative age effects on slope. Basically, no significant effect of age on rate of change, but a trend to a reduction in use over time after your earlier experimentation. And the fact that under the specific constraints I mentioned and haven't yet discussed, you can get very similar results across these three approaches means that it is sort of up to you mostly which higher order growth model you prefer. Now, we'll take a look at some empirical examples of higher order growth models. So when do people use these? Let's look at a few examples from the resources for this week. The first paper by Aileen Sayer is more of an educational textbooky chapter, and this is a curve of factors model. In grades 5, 6, 7, 9, and 10, they measured students' expectancies for academic performance in 3 indicators, and at each occasion they created a time-specific factor. Note too at the bottom, because the lower order factors aren't growth models, they allowed the indicators to correlate with themselves over time. Then, on top of these time-specific factors, they built a curve of factors. And this is kind of a nice hybrid because you see an intercept and slope, and then you see a third factor that posits extra growth, added growth in the final 2 waves. We've done those models before and called them piecewise models. So this is both a piecewise model and a curve of factors model. I don't love how they tabled this up. But basically in red are the fixed intercept, slope, and increment. In blue is the random variance of intercept, slope, and increment. In green is the covariance among the 3 factors. Everything was significant here. So that was curve of factors. This paper, which includes Markolides, an SEM textbook writer I've mentioned a few times in Multivariate, is a simple 2-outcome associative model. What's interesting here, and a demonstration of how flexible these models are, is that they had different numbers of measurements for the 2 constructs. First, they had math motivation measured when children were 9, 10, 13, 16, and 17, not equally spaced, something they cleverly tried to convey in the path diagram. And I believe the numbers refer in this example to the age of the kids. So math motivation at age 9, age 10, and then as you can see, it's not equally spaced time, so at age 13, 16, and 17. Second, they had math achievement. Because this came from a standardized school-based assessment, for this they had annual assessment, including years in which they could not collect motivation. So they both cover the same time span, but the achievement factor has a lot more occasions to it. So it'll be more reliable, and we'll have more information about change. But there's no reason you can't do this, have these different time scopes. And putting them together, this is the associative model, double-headed arrows, linking growth in the 2 construct. Does the rate of change in your motivation relate to the rate of change in your achievement? And so again, what you have here is yet another model for presenting this. This is why I keep wanting to show you these different models. And here's another blast from the past. Notice that for both some of the math motivation occasion and some of the math achievement occasion, the loadings are asterisked. They are estimated, not fixed, and thus have significance tests. This immediately tells us that this is a Meredith and Tesack latent basis model. So these authors have taken a more exploratory approach and let the data define time structure. So then, when we look down at the covariances, because that's clearly what they've chosen to present, these aren't standardized correlation, we see that the 2 intercepts are significantly related. Probably more importantly, the 2 slopes are significantly related and positively. So the more increase in motivation, the more your increase in achievement. And there's a little bit, although this wasn't explicitly constructed to do cross-lag. There's a little bit of a hint of a cross-lag, and what do I mean by that? I mean that motivation level is not a significant correlate of achievement rate of change, but achievement level is a significant correlate of motivation rate of change. Now, if you remember what I said to you a few slides back, because there are more occasions for achievement than there are for motivation, and achievement slope is actually more reliable, it has more variance and is easier to predict. So in that context, the fact that achievement level predicts motivation slope, but motivation level does not predict achievement slope, goes in the opposite direction of the reliability, so it's even more impressive. It really does make it look like, and you can't say too strongly because we haven't done the formal appropriate test, but if you're going to take a bet on resolving the chicken and egg question here, that high achievement predicts later higher motivation more than the reverse. So one more example of these higher order models, which happens to come from my domain, from a longitudinal study of aging in Australia. And one of the things they did in this longitudinal study was that they measured a lot of things. And they had 1,045 Australians aged 70 and older, and they measured them in 1990 and then 3 subsequent occasions. The paper uses a factor of curves latent growth model to examine the existence of a common factor responsible for age-related deterioration in cognitive and non-cognitive processes. There's a famous question in cognitive aging research that asks, does it all go together when it goes? The idea that this is that aging constitutes a global unitary process that drags everything down with it. Now, while that's probably not absolutely true, it is interesting to see if decline in disparate cognitive, motor, and sensory functions might all be coupled. Factor of curves is a way of addressing that question. In other words, if you find a common decline process that transcends now not just multiple forms of cognition, but also other non-cognitive, say, physical domains, then you may have identified a global aging process that suggests it does, at least at some level, all go together when it goes. So they had lots of different things that they measured. They measured a common gene whose allele is associated with higher risk of Alzheimer's disease. And I put this here in the lower right to remind us just to say that in a study like this, when you have dropout, all of these studies, it's important to quantify and characterize the dropout. And you'll notice, and this is something I'm seeing more and more in these multi-occasion longitudinal studies, is that they develop different models for dropout at each occasion because there are usually different processes that explain early versus late dropout. We'll revisit that idea a bit in our Missing Data Week. So there's a lot here, but it's easy to see. Starting at 1 o'clock and wrapping around to 11 o'clock are 5 separate linear growth curves for the cognitive variables of reaction time, speed, a sensory variable, the motor variable of grip strength, and the cognitive variable of memory. And all 3 curves load on a common intercept and slope, and hence its factor of curves. And interestingly, then they try to predict this common does it all go when it goes factor with a variety of risk factors, including age, the gene marker for cognitive impairment, education, a measure of reading level, and sex. They present spaghetti plots for each of their 5 growth models. These are based on the raw data, which is why we see some nonlinearity in some cases, even though the model itself is linear. And interestingly, even though with only 3 occasions they estimated an occasion basis model, we see that the graphs here are age basis. I've skipped some tables because this is the interesting one. They showed the standardized betas of each lower order growth process on the higher order intercept and slope. And unlike Bolin and Coran's associative model, which included some constraints so they could compare different models, no constraints were imposed here. Thus, they could comment on which variables seemed to load more highly on the common intercept and slope, which had weaker relationship, and they also reported the effect of their 5 covariates on the higher order growth factor down at the bottom. So this is a nice way of showing, for example, that the common factor level was more closely related to the non-cognitive variables of grip strength and sensory functioning, but the common factor rate of change was more closely related to the 3 cognitive variables. There is a lot more of interest in this table, but I don't want to dive too deeply into this right now. But just to illustrate that they could accomplish a lot with this model, how they reported it. Next week, we'll actually run these, and you can get a better feeling for how to do them and what they mean.